Hi, I'm mducasse, a 5th year EE major CS minor. This is the final demonstration of my senior project, the SeeStar III Sensor Module. SeeStar is an autonomous camera system designed to photograph deep ocean ecosystems. In its first two iterations, the SeeStar system consisted of a camera module featuring a GoPro camera, microcontroller, and digital storage, as well as an LED module to provide lighting and a large battery to provide the system with months of power. The system usually operates from a stationary rig on the ocean floor, where it captures photo and video recordings of the aquatic environment on a pre-programmed interval over the course of several months. At the end of its deployment, the system is retrieved and the images on its internal storage can be inspected and archived. The latest iteration of the SeeStar features a sensor module that can interface with an array of aquatic sensors. These sensors supplement the photo and video captures with other data like temperature, pressure, pH, and salinity. My role in the project was to design the software for the sensor module, allowing it to interface with several sensors and providing flexibility for multiple configurations. In addition, I implemented a serial communication protocol to allow the camera module to pull the sensor module for sensor data or to adjust calibration and configuration parameters. From a software standpoint, the sensor module has a series of data structures called channels that each can be configured to interface with a given physical sensor, regardless of the sensor's type. Each channel has a corresponding config file in the system's SD card to tell it what type of sensor it's interfacing with. In addition, the config file will give the channel information unique to its sensor, like which Arduino pins the sensor is connected to. The image here shows an example of a config file that would be used to configure channel 2 to use the SPI temperature sensor. It also lists the sensor's thermocouple. It also lists that the sensor's thermocouple would connect to pins 40, 41, and 43 on the Arduino. Upon startup, the Arduino reads this file and configures the channel accordingly. The system is currently compatible with 3 sensor types. The first is the RBR real-time temperature sensor that interfaces with RS-232 serial. The second is a temperature sensor that interfaces with the Arduino with a thermocouple via SPI. The third is an analog pressure sensor, and it uses an ADC to communicate with the Arduino via I2C. The software has a generic measurement function such that any channel can be pulled for data with the same way regardless of its sensor type. The function actually contains a switch statement that evaluates the channel's sensor type parameter and calls the measurement function unique to its sensor type. However, the unique function must be designed to read the sensor and convert its sensor to string format, both for saving to the sensor module's SD card and for serial transfer back to the camera module. This function prototype shown must be used for any sensor's measurement function to ensure compatibility with the system. The system currently supports commands for reading data from a given channel or reading data from all channels at once. Next, I'm going to show a video demoing how I can enter the measurement command into the Arduino terminal to record data from the temperature sensor. To prevent unnecessary power loss, all sensors need to be powered down when they aren't gathering data. This is achieved by switching the sensor's positive power terminal with a relay. Each of these relays are actuated with a DIO pin on the Arduino. Next, I'm going to show a video where I enter the power channel and power all commands to open and close the relays on the relay board. The challenge in designing the SeeStar software was allowing for flexibility and compatibility with multiple sensor types while making setup and use as user-friendly as possible. One goal was to create a generic framework that I could interface with any new sensor with little or no additional code. Unfortunately, it is infeasible to generalize all sensors with one interface, so I did the best that I could to write a generic infrastructure to allow for integration of new sensors with the least amount of code possible. I designed the system to use a data structure called SSM, or SeeStar Sensor Module, to contain all of the important information pertaining to each of its sensors. This structure keeps track of what channels are using what sensors, what pins those sensors are connected to, what baud rate is used in communication, etc. The top level of the struct contains an array of channels. Each channel contains a variable indicating what type of sensor it's using, and a union called sensor. A union in the C language is a variable that can store more than one data type. I use this union to store one of many structs that are designed to represent each of the physical sensors I've integrated into the system. The figure shows that channel 0 is using an RBR serial sensor. Whoops. Here we go. Here are the three structs that I use to represent each of the physical sensor types in the code. Notice that each struct holds information that is only pertinent to that sensor type. For instance, notice that the serial sensor, representing the RBR temperature sensor, includes a baud rate value, since baud rate is only used in serial communication on the Arduino. Another thing to notice is that the I2C and SPI structs have pointers to the Adafruit ADS1115 and the SparkFun Max 31855K objects. Since these sensors come with third-party software drivers, I just point to their driver classes from their structs, and I use them to call their measurement functions from within my own measurement function. On the bottom right, there is an implementation of the sensor union, with a field for each of the three sensor structs I've implemented. It also accepts the type child SSM, which would mean that a channel is connected to an entirely different sensor module, but I didn't have the hardware to fully implement that feature in my senior project. Integrating new sensors requires additional code in three places in the sensor module software. First, the user has to decide what sensor parameters would need to be known during the system's runtime, and design a new sensor struct to store those parameters. Next, the user would need to write a function to read those parameters from a config file into the struct. I already have low-level functions for parsing config files, so this wouldn't be too difficult. Finally, the user would need to design a function for reading the data from the sensor with the function prototype I described earlier and converting it to string format. Once this is all done, the system will be ready to interface with the new sensor. The full procedure for integrating new sensors is described in Appendix B of my senior project report. When scoping my project, we decided upon a set of commands that the camera module could send to the sensor module. However, I was only able to implement some of these. The camera module currently doesn't have the ability to read or write to the calibration or configuration settings of any of the sensors. I also would have liked to implement a feature to synchronize the sensor module's clock with the camera module's, since the clock is susceptible to drift. In addition, the Arduino platform chosen for the sensor module draws between 50 and 100 milliamps depending on power mode, which is far too high for a battery-powered application. I expect that the next student to work on SeeStar will port the software to a more efficient platform like the Feather M0. That concludes my senior project presentation. Thank you for listening.